Hey everyone, and welcome to The Explainer. We're setting the stage today for a truly revolutionary shift in how we think about artificial intelligence. We're finally moving away from this old assumption that frontier AI needs to be tethered to massive, energy-hungry cloud servers. Instead, we're stepping right into the era of hyper-efficient, brain-inspired, local operating systems. It's an absolutely fascinating shift.
Okay, let's dive into this. We've all gotten so used to the idea that powerful AI requires warehouses full of GPUs and these enormous, loud cooling systems. But what if that simply isn't true anymore? What if the future of frontier intelligence is actually small enough to fit right on your desk, running completely off the grid? Well, to understand how we actually get there, we first need to look at the massive roadblocks standing in our way.
Take a look at this jarring number, 1.287 gigawatt hours. That is the amount of energy required just to train a traditional model like GPT-3. To put that into perspective for a second, that's the equivalent of the power consumed by 120 average households over an entire year. The classic AI approach is incredibly powerful, no doubt, but it's an absolute Goliath when it comes to energy consumption. It just doesn't scale for the billions of edge devices out there.
So if cloud transformers are the Goliath, constantly awake, wasting massive amounts of energy, basically just multiplying zeros, then our David in this story is the edge spiking neural network, or SNN. SNNs are entirely event-driven. They use temporal encoding, meaning they only process data when an event actually happens in real time, just like the neurons in your actual brain. This makes them up to 100 times more efficient than classical AI architectures.
Here's a quick look at our agenda. 1. The energy problem of classic AI. 2. The 100 times more efficient SNN solution. 3. AI builds its own OS. 4. GoldWorm's direct hardware control. 5. Scaling from LLM to SNN. And finally, 6. Why SNNs dominate the market.
Let's start with Section 1, the energy problem of classic AI.
Now, what's really interesting about this slide is the stark contrast in how these two systems actually activate. Traditional artificial neural networks are permanently active. Think about it. Every time you ask a question, millions of dense math operations happen, regardless of whether that specific parameter is even relevant. SNNs, on the other hand, are sparse. Because they use temporal encoding, a neuron only draws power and fires when a specific electrical threshold is crossed. No threshold? Absolutely no power drain.
Moving on to Section 2, the 100 times more efficient SNN solution. This biological inspiration brings us to a really fascinating architecture known as the GoldWorm project. So what exactly is a spiking neural network? Well, think of it like your brain's auditory neurons. If you hear a loud noise, your brain's auditory neurons spike. If the room is quiet, they do nothing. SNNs do exactly this, but in silicon. They don't waste precious compute cycles analyzing silence.
And the results of this architecture are absolutely staggering. We are talking about under 5 milliseconds of latency, running on a mere 0.5 watts of power. Because it uses this highly efficient, sparse communication protocol, it is utterly untethered from a data center. It thinks and it reacts in real time right there on the edge device.
Next up, Section 3. AI builds its own OS.
Let's move to and see how this builds, because GoldWorm isn't just an efficient network. It's a massive paradigm shift. It takes AI from a passive tool you just type prompts into and turns it into an active, autonomous operating system. This system basically acts as a central nervous system. First, perception. It constantly analyzes high-frequency signals like server logs or audio streams. Then, reflection. It simulates possible solutions. Next, memory. It checks past experiences in its local graph. And finally, action. It executes commands autonomously via APIs. It perceives, it thinks, it remembers, and it acts.
The memory aspect here is particularly brilliant. The architecture uses a local retrieval augmented generation, or RAG, pipeline, seamlessly integrated with Obsidian, which is a local markdown notes app. This effectively acts as the AI's long-term memory vault. It completely bridges the gap between raw physical perception and high-level abstract thought. If it detects a system error, it can instantly retrieve your personal troubleshooting notes, read them, and even write new solutions back into the vault. And crucially, this entire high-level thought process happens entirely without internet access.
Let's look at Section 4, GoldWorm's direct hardware control.
So a cognitive loop is great, right? But to be a true operating system, it needs to touch the physical world.
And because the system requires so little power, it can run as a local central nervous system right on your machine. It monitors your microphones, telemetry, and system logs in real time. This opens up incredible real-world applications with a strict, baked-in zero data leakage guarantee. Just imagine autonomous offline robotics in a factory or a secure local workflow orchestrator that actively manages your network resources without ever sending a single byte to the cloud.
Underpinning all of this is a really unique data structure called the Zero Trust Connectome, or .ztc. This isn't just a regular neural network file. It's a cryptographic, self-healing topological graph. If the AI detects a semantic contradiction in its own logic, it actually traces back its decision history using Merkle trees and autonomously self-repairs. It makes every single decision completely auditable and transparent. There are literally no black boxes here.
Section 5. Scaling from LLM to SNN.
So the crucial point is, how do we actually get frontier-level intelligence into these tiny networks? Well, the answer is a process called double sparsity. We can take a massive open-source large language model and run it through a conversion pipeline. We literally prune away 80% of the weights, the weakest connections, leaving only the most critical 20% active. We then translate those remaining weights into exact threshold triggers for our spiking neurons. It's like distilling the brain down to its absolute essence.
The impact of this conversion is staggering. I mean, look at this. A dense 32 billion parameter model normally demands a whopping 64 gigabytes of RAM. But once it goes through this conversion and compression, that exact same intelligent model shrinks down to require only 8 gigabytes of RAM.
And what does that extreme compression actually mean in the real world? It means you can take a highly capable, multi-billion parameter model and run it natively and rapidly on cheap consumer hardware. You can deploy this entire brain-inspired OS on a $60 headless Raspberry Pi 5. It processes sensors, audio, and complex logic right there on the edge, utterly independent of the internet.
Finally, Section 6. Why SNNs dominate the market.
When you combine this kind of extreme efficiency with complete auditable integrity, it fundamentally changes the market landscape. Classical AI simply cannot solve the pain points of certain critical industries, but SNNs definitely can. In defense and aerospace, systems require strict air-gapped deployment and fully auditable decision chains. In Industry 4.0 and IoT, you have billions of sensors severely limited by battery life, so 100 times energy savings is a total game changer. And in healthcare, real-time zero-latency diagnostics with zero data privacy risks are absolutely essential. SNNs perfectly fit all these constraints.
This quote perfectly summarizes the ultimate strategic advantage of the GoldWorm architecture. Autonomous decisions with verifiable integrity, under 5 milliseconds and 0.5 watts. It's not just a chat interface anymore. It's an intelligent, reactive entity physically and digitally anchored to its environment.
We are really stepping out of the sandbox now. AI is evolving from a passive cloud service into a deeply embedded local cybernetic system. So I want to leave you with this question to chew on. When your AI acts as a localized, independent brain that you completely control, what will you build with it? Thanks for joining me on this explainer. I'll catch you next time.